The night sky has always held a certain mystique, but few sights inspire such awe and wonder as the Aurora Borealis, the northern lights. Imagine standing on a remote snow-covered plain, the air crisp and cold. Above you, the sky erupts in a symphony of colour. Shimmering curtains of green and blue dance across the horizon, sometimes tinged with vibrant hues of pink and violet. In the heart of our solar system lies the Sun, a churning ball of plasma that constantly bombards our planet with a stream of charged particles known as the solar wind. This solar wind, travelling at incredible speeds, would strip away our atmosphere and make life on Earth impossible were it not for our planet's magnetic field. However, some of these charged particles manage to penetrate this magnetic shield, funneling down towards the Earth's poles. When these charged particles collide with oxygen and nitrogen atoms in our atmosphere, they transfer their energy, causing the atoms to become excited. This is the ethereal glow we perceive as the northern lights. The northern lights offer scientists a unique window into the dynamics of our planet's upper atmosphere and the complex interplay between Earth and the Sun. By studying the aurora's intensity, colours and patterns, researchers can glean insights into the density and composition of the upper atmosphere. The same solar storms that trigger these dazzling displays can also disrupt our technological infrastructure. Understanding these space weather events is crucial for mitigating their potential impact on our increasingly technology-dependent world. The Aurora Borealis represents a captivating blend of scientific inquiry and aesthetic appreciation. Our journey to understand the Aurora Borealis begins with the Sun, a celestial powerhouse that constantly emits a stream of charged particles known as the solar wind. Were it not for Earth's magnetic field, this relentless bombardment would strip away our atmosphere. Some of the solar wind particles are funneled down towards the polar regions, where they encounter the upper reaches of our atmosphere. As the charged particles from the Sun collide with atoms and molecules in our atmosphere, they transfer their energy. This collision sets in motion a chain reaction, a celestial dance of energy that ultimately gives birth to the ethereal glow of the northern lights. The energy imparted by the solar wind particles to the atoms in our atmosphere is not without consequence. These atoms become energized, their electrons jumping to higher energy levels. As the electrons return to their original lower energy levels, they release the excess energy in the form of light. This release of light is what we perceive as the Aurora Borealis. The color of the light emitted depends on the type of atom involved in the collision and the altitude at which the interaction occurs. The vibrant emerald green that often dominates the auroral display is a signature hue of excited oxygen atoms. This particular shade of green arises from a specific transition within the oxygen atom, releasing a photon of light with a wavelength that our eyes perceive as green. At lower altitudes, around 60 miles above Earth's surface, oxygen atoms collide more frequently, resulting in the brilliant green hues. However, as we ascend higher into the atmosphere, the density of oxygen decreases and collisions become less frequent. At these higher altitudes, above 100 miles, oxygen atoms release their excess energy, producing a rarer, redder hue. While oxygen may be the prima donna of the auroral ballet, nitrogen also plays a supporting role, adding its own palette of colors to the celestial display. When nitrogen molecules are struck with sufficient force by solar wind particles, they become energized. As these energized electrons return to their ground state, they release their excess energy as a spectrum of hues ranging from blue to violet. These nitrogen-induced colors are often more elusive than oxygen's characteristic green, appearing as fleeting accents. The exact shades of blue and violet produced depend on the energy of the initial collision and the specific transitions within the nitrogen molecule. The Aurora Borealis is not merely a celestial light show. It provides scientists with valuable insights into the intricate workings of Earth's upper atmosphere. The aurora acts as a luminous tracer, illuminating the invisible flows and revealing the hidden dynamics of this remote realm. By analyzing the colors, shapes, and movements of the aurora, scientists can infer the density and temperature of the upper atmosphere. The aurora's dynamic nature reflects the constant interplay between the solar wind and Earth's magnetic field. The dance of the Aurora Borealis is intricately linked to the ebb and flow of the solar wind. During periods of heightened solar activity, the solar wind intensifies, carrying with it a surge of charged particles. This surge can trigger geomagnetic storms, disturbances in our planet's magnetic field that manifest as spectacular auroral displays. As the solar wind intensifies, the tempo of the aurora quickens, its movements becoming more frenzied, its colors more vibrant. Scientists, by studying the aurora's response to the solar cycle, can gain a deeper understanding of the sun's behavior and its impact on our planet. The Aurora Borealis is an active participant in the dynamic interplay between Earth and the Sun. It serves as a celestial alarm bell signaling the arrival of a geomagnetic storm. These geomagnetic storms can disrupt satellite communications, induce currents in power grids, and pose risks to astronauts in space. Scientists, by monitoring the aurora's behavior, can anticipate and mitigate the impacts of space weather events. The aurora's intensification serves as early warning signs, providing valuable time for protective measures. Auroras are not unique to Earth. They occur elsewhere in the vast expanse of the universe. Any planet or moon with an atmosphere and a magnetic field can host its own auroral displays. Jupiter boasts auroral displays that dwarf our own in both size and intensity. Saturn, adorned with its majestic rings, puts on its own auroral show. Even Mars exhibits faint auroral emissions, hinting at a more dynamic past. The Northern Lights, or Aurora Borealis, are a celestial spectacle in the northern skies. Their twin, the Southern Lights, or Aurora Australis, graces the southern polar skies. These twin auroras are two sides of the same cosmic coin. Solar wind triggers auroral displays at both poles simultaneously. Earth's magnetic field lines stretch from pole to pole. Solar wind strikes these lines, setting them vibrating. These vibrations energize gases, triggering auroras. Northern and southern lights are not always identical. Differences in Earth's magnetic field cause variations in auroras. As if the Aurora Borealis and Aurora Australis weren't enchanting enough, nature, it seems, has a penchant for celestial surprises. Enter Steve, an enigmatic atmospheric phenomenon that, while resembling an aurora, stands apart as a distinct entity. Steve, short for Strong Thermal Emission Velocity Enhancement, first came to scientists' attention in 2016 thanks to citizen scientists. This ribbon, unlike typical auroras, appears as a narrow arc, often with green picket fence-like structures. Intrigued, scientists turned their instruments towards the sky, eager to unravel Steve's mysteries. What they discovered only deepened the enigma. Unlike auroras, Steve appears to be caused by intense heating of the upper atmosphere. Imagine a celestial paintbrush heated to incandescence, trailing purple light across the night sky. The exact physics behind Steve's formation remains an active area of research. Scientists believe it involves the interaction between Earth's magnetic field and hot plasma in the ionosphere. Steve highlights the dynamic and surprising nature of our planet's upper atmosphere. It reminds us that even in well-studied atmospheric physics, new phenomena await discovery. Chasing the Northern Lights, a journey of patience and preparation. Witnessing the Aurora Borealis is an experience etched in memory, a testament to the awe-inspiring beauty of the natural world. Chasing the Northern Lights demands patience, preparation, and a healthy dose of luck. Imagine yourself bundled in layers of warm clothing standing on a windswept plain, your gaze fixed on the northern horizon. Excitement surges as the glow intensifies, transforming into a shimmering arc, a celestial curtain drawn across the heavens. Prime time for auroral displays. When and where to seek the elusive glow. The Aurora Borealis, while active throughout the year, is a fickle performer. To maximize your chances, understand the prime time and locations for optimal viewing. The aurora graces the skies within the auroral oval, a ring-shaped region around Earth's magnetic North Pole. This oval expands and contracts with solar activity, shifting southward during geomagnetic storms. Certain locations within this oval are prime aurora viewing destinations. Fairbanks, Alaska is known as the aurora capital of the world. Yellowknife, Canada offers a pristine setting far from city lights. Tromsø, Norway combines stunning auroral displays with breathtaking fjord landscapes. The optimal viewing season runs from late August to early April. Venturing into the realm of the Aurora Borealis requires practical preparation for comfort and safety. Warm clothing is paramount, as temperatures can plummet far below freezing. Layers trap heat and wick away moisture. Don't forget a hat, gloves and a scarf. Waterproof boots provide traction and insulation. A headlamp is invaluable for navigating dark trails. A DSLR or mirrorless camera captures the aurora's beauty. A tripod stabilizes your camera during long exposures. Allow your eyes to adjust to the darkness. Scan the entire northern sky. And most importantly, be patient. As we conclude our exploration of the Aurora Borealis, we find ourselves drawn back to that primal fascination, that sense of awe and wonder that has captivated humanity for millennia. The northern lights, for all our scientific understanding, retain an aura of mystery, a reminder that the universe still holds secrets waiting to be unveiled. We've journeyed from the heart of the sun, tracing the path of the solar wind as it races across the vast expanse of space, carrying with it the energy that fuels the auroral display. We've delved into the intricacies of Earth's magnetic field, that invisible shield that protects us from the sun's fury while guiding a select few of its charged particles towards our poles. And we've witnessed, through the lens of both science and art, the ethereal beauty of the aurora itself, its shimmering curtains of light, its pulsating glows, its ever-changing palette of colors. We've come to understand that this celestial ballet is not merely a visual spectacle. It's a testament to the fundamental laws of physics that govern the cosmos, a dance of charged particles and atmospheric gases orchestrated by the interplay of Earth and the Sun. Yet, for all our knowledge, the aurora retains its power to inspire awe, to evoke a sense of humility in the face of the vastness and mystery of the universe. It reminds us that we are part of something much grander than ourselves, a cosmic tapestry woven from starlight and solar wind, magnetic fields and atmospheric gases. The Aurora Borealis, in many ways, embodies the harmonious interplay between science and wonder, a testament to our innate curiosity about the world around us and our capacity to appreciate its beauty, even as we strive to understand its complexities. Science, with its meticulous observations, its rigorous experiments, and its elegant theories, has provided us with a framework for comprehending the aurora's mechanics, for tracing the flow of energy from the sun to Earth's upper atmosphere, for deciphering the language of light emitted by excited atoms. But science, in its quest for knowledge, does not diminish the aurora's capacity to inspire awe. If anything, understanding the intricate interplay of forces that give rise to this celestial display only deepens our appreciation for its beauty, its ephemeral nature, its connection to the cosmos. The Aurora Borealis, therefore, stands as a bridge between the realms of science and wonder, a reminder that the pursuit of knowledge and the appreciation of beauty are not mutually exclusive endeavors, but rather complementary aspects of the human experience. It encourages us to embrace both the analytical rigor of the scientist and the childlike wonder of the artist, to marvel at the universe's mysteries while seeking to unravel them, to find beauty in the intricate workings of nature while acknowledging the vast unknown that still lies beyond our grasp. As we bid farewell to the Aurora Borealis, we do so with a sense of gratitude for the opportunity to have witnessed its ethereal beauty, to have glimpsed, however briefly, the intricate workings of the cosmos. The aurora, like all celestial phenomena, is a reminder of our place in the grand scheme of things, a testament to the interconnectedness of all things. The same solar wind that fuels the auroral display also bathes our planet in life-giving light and warmth. The same magnetic field that guides charged particles towards our poles also protects us from the sun's harmful radiation. And the same atmospheric gases that glow with such vibrant hues also sustain life as we know it. The Aurora Borealis, therefore, is not merely a distant spectacle, a celestial sideshow to be observed from afar. It is an integral part of our planet's story, a reminder of our intimate connection to the sun, to the cosmos, to the very fabric of the universe. As we gaze up at the night sky, let us remember that we are witnessing a timeless dance, a celestial ballet that has been playing out for billions of years, a testament to the enduring power and beauty of the universe. And let us carry with us a sense of wonder, a thirst for knowledge, and a deep appreciation for the delicate balance of forces that make life on Earth and phenomena like the Aurora Borealis possible.